So welcome to this lecture. Today I am going to solve a integral using counter integration. So the question is we have to solve this 0 to infinite sine square mx divided by x square plus a square dx. This is the integral, so we have to prove this equals to this number. Okay, so this is the problem. So to solve this, we are going to use the concept of contour integration, and we can't solve this directly, so we need to we need some rearrangement in this integral. For this I am going to use the Leibniz theorem, that is the differentiation under the integral sign. So let's call this let's call this be I of m. Okay, I am going to differentiate this with respect to m. So I dash m equals to d by dm of 0 to infinite sine square so because the limits are independent of m, so we can take this differentiation under the integral. So 0 to infinite okay. So what's the differentiation of sine square mx with respect to m? It's going to be 2 sine mx cos mx, and then by chain rule differentiation of mx is going to be x. Okay, cancel this x with this. Use the double angle formula for sin x, that is sine of 2 times m of x x square plus a square. So dx is here. Okay, this is what we get I of m. So we can solve this integral using counter integral method. Let's consider the function. That is f of z equals to e raised to power I times 2 m of z divided by z square plus a square. Okay, so what I am going to do, I am going to solve this complex integral. Let's call this one, and we have considered the function. Let's find its poles. Sorry, not integral sign here. Poles of f of z are. We can write this as it is. Let me like z minus iota I, z plus iota I. Okay, clearly z equal to 0, z is equal to iota I are simple poles. Okay, let's draw the contour. So I am going to take a contour in such a way that the 0 is not the part of that contour. So let me start this like this. Okay, So we are going from minus r to plus r. 0 is here. Let's call this be gamma. Sorry, we are going to use this direction like this. Okay, this is gamma, this is small gamma. Let's call this minus r, this is r. So clearly minus iota is lying outside the contour, while iota is lying something here. Okay, so let's use the Cauchy residue theorem to calculate the integral of this function. 2 pi iota sum of residues. This is the Cauchy residue theorem. Okay, now so because the iota is the only pole lying inside the contour, so we are going to find the residue only at iota of A. So I am going to write residue like this: f of z when z is equal to iota A. Okay, so limit z is tending to iota A, z minus iota A, f of z. This is the formula to calculate residue. Okay, limit z is tending to iota A, z minus iota A. What is f of z? F of z is going to be e raised to power iota 2 mz divided by z, z minus iota A, z plus iota A. Let's cancel this. Okay, put the limit. We get iota 2 times m of iota A divided by iota A 2 times iota A. Okay, solve this. This is going to be iota into iota minus 1, that is minus 2 ma. What about this? Iota into iota is minus 1, that is minus 2a square. Okay, this is the required residue. So by Cauchy residue theorem, what will be this function under the integral of complex line? We get 2 pi iota sum of residues. Okay, let's cancel this 2. Okay, that is minus of pi times e raised to power minus 2 ma divided by a square, and iota is here. Okay, this is the our integral. Now just look at this complex integral. This is nothing but the integral of our function from minus r to positive r. This is I am writing from contour. So this is okay. So at the real line, at this from minus r to r, what will be z? Z is equal to x plus iota y. But at this line y is 0, so z is equal to x, and dz is equal to dx. So we can write here f of x dx. So after that we are going from small gamma f of z dz. After that small r to r f of x dx, and after that we are going through capital gamma f of z dz. Okay, so let me call this equation 2. We are going to solve each integral step by step. First of all, we are going to solve this one. Okay, let's call this be integral gamma f of z dz. So I am going to use here Jordan lemma. What is our function? Our function is f of z equal to e raised to power iota m z divided by z square plus e square. Okay, clearly limit z is tending to infinity 1 upon z square plus e square is equal to 0. So by Jordan lemma, limit z is tending to infinite e raised to power 2 iota mz divided by equal to 0. Okay, so when the limit z is tending to infinity, this number is going to be 0. Okay, now we are going to solve small gamma, which is nothing but okay, e raised to power 2 iota mz z upon z square plus e square dz. Okay, so there is a theorem to solve this number. For this I have to calculate the limit of z is tending to 0, z of f of z, which is limit z is tending to 0, z of e raised to power iota 2mz z minus a z square plus e square. Okay, let's cancel this z. So put z equal to a, z equal to 0, e raised to power 0, 0 square plus e square. This is 1 by a square. Okay, the theorem is limit z is tending to 0, integral f of z dz under the small gamma is equals to iota theta 2 minus theta 1 times the value of that limit we have calculated the earlier. So what is theta 2 and theta 1 here? So our contour is looking like this. Basically we are going from this to this. So theta 2 is 0 because we are moving from angle 0. So theta 2 is 0 and theta 1 is pi because we are moving from this to this. So theta 2 is 0 and our theta 1 is pi when we have completed the half circle. I am talking about small gamma. So this is going to be iota times 0 minus pi into L. What is the value of L? It is 1 by a square. So it is going to be minus iota pi upon a square. Okay. So we have calculated the small integral as well as we have calculated the integral over small gamma as well as over capital gamma. So now let's move on our equation number 2. So we have done this one as well as this one. These are remaining. So let's take limit capital R tending to infinity and small r tending to 0. This is going to be f of z over the complex line or complex contour, whatever you want to say, equals to minus infinity to 0, then here f of x dx plus. So when the r is tending to 0, this number is going to be this one. So I'm going to write this instead of that integral. After that, in next integral, the limits are from 0 to infinite, f of x dx. And what is the value of this? This is we have calculated 0 by Jordan lemma. Okay, these are the integrals we all got at the last. Let's combine these two. This is going to be minus infinite to infinite f of x dx minus iota pi divided by a square. We have also calculated the value of this using the Cauchy-Residue theorem. So I am going to plug in that value here. What is the value of this? This value is here it is. So put this value here, that is we are going to minus 2ma minus 2a square. Is there any pi or iota here? Sorry, we plug the wrong value. This is the value, not that. Minus iota pi e raised to power minus a square. Okay, I'm going to move this one in left hand side, so we get this. Okay, let's call this the equation number 3rd. So our f of x is e raised to power 2 iota mx divided by x multiplied by x square plus a square. What we are going to do here, we are going to compare real and imaginary parts of this equation. So let's compare. This is going to be minus infinite to infinite. F of x is this, so I can write this as cos of 2mx plus iota sine 2mx divided by x times x square plus x a square dx equals to iota pi by a square minus iota pi by a square e raised to power minus 2ma. Okay, so comparing imaginary part, we get integral minus infinite to infinite sine 2mx x upon x square plus a square equals to iota pi a square minus iota pi a square. Okay, let's call this be equation 4. Okay, so what is this number? Let me recall you where I have started. Here it is, this from equation 1, but it is from 0 to infinite, so we have to check this function. Let's call this g of x. Let's put x instead of minus x. We get sine of 2 times minus x, that is minus, and here also minus x square plus a square. This is nothing but g of x. So do you remember the property of the integral? Integration from minus infinite to infinite f of x is same as 2 times integral 0 to infinite f of x dx if f of minus x is equal to f of x. So I am going to use this here. Okay, so let's start. This is going to be integration 2 times 0 to infinite sine 2 mx divided by x upon x square plus a square. Okay, we have compared the imaginary part, so I done a mistake in equation number 4. So in equation 4 we have to remove this iota because we have compared the imaginary part, so there is no need to write iota here. It's okay. So let me rewrite that equation again. This is going to be pi by a square minus pi by a square e raised to power minus 2ma. Okay, so from the equation 1, this is nothing but I dash m. Okay, what we wanna calculate? We wanna calculate I of m, not the I dash m. So let's integrate this with respect to m. This is going to be 2 times I of m pi by a square into m minus pi by a square e raised to power 2 times m of a. Here we get 2 times of a plus some constant. Okay, so we need to calculate the value of c. For this, let me start again. I of m is nothing but integral 0 to infinite sine square mx divided by x square plus a square dx. So what is I of 0? This is nothing but sine square 0 of x square plus a square dx. This is going to be 0. So when I of 0 is 0, so put, let me call this equation 5. Put m equal to 0 in 5. So 2 times I of 0 is nothing but pi by a square multiplied by 0 multiplied by pi by a square, sorry, okay, e raised to power 0 minus 2a plus c. So this is nothing but 0 equals to minus pi by a square. E raised to power 0 is 1 minus minus plus, that is 1 by 2a plus c. So c is nothing but pi by 2 times a cube, pi by 2a cube. That's all. Put this in equation 5. What we get? We get 2 times I of m is equal to pi by a square and minus pi by a square e raised to power minus 2ma divided by minus 2a. What is the value of c? That is plus, it is in minus, sorry, the value of c is in minus. I have done a mistake. So here we get a minus sign. I forget to put the minus sign, so sorry for that. So let's put the value of c, that is minus pi by 2 times a cube. So what we have to prove? We have to prove this result. This result we have to prove. Okay, so pi by 4a cube, we have to take this common. So let me take pi raised to pi divided by a cube times 4 common. So because we have taken pi by a cube, so here is a square, we get a times m. There is no 4 here, so we will put, okay, what from this we get pi by a cube, okay, 2 1 2 minus 2 times e raised to power minus 2ma and minus 2. Let's divide both sides by 2. Let me common out 2 as a factor. Here we get 2am minus e raised to power 2ma minus 1. So cancel this. am minus e raised to power minus 2am minus 1. I think this is the result we have to prove. I think I have done a mistake. Yeah, here is the mistake. This minus sign will be cancelled out by this. There is a plus sign. Okay, so here is a plus sign. This is the required result. Yes, that's it. Thanks for watching.